Up to this point, we have talked about experiments with only one factor. Now we will expand that to more than one factor. Each factor will be denoted by a capital Roman letter, A, B, C, etc. The number of levels associated with it will be represented by the respective lowercase letters, A, B, C, etc. The number of levels for each factor does not need to be or usually isn't the same. Notice that the setup on the slide is for a two-factor experiment. Also, each treatment combination is represented by a cell, with the corresponding observations within the cell. This is a completely randomized design because we assume that runs are made in a random order. The effects model for the two-factor case is given on the slide. Notice that we have two effects instead of one. Also, we have an effect for the combination of the two, which of course is what we call an interaction. The model assumptions here are no different than in the single-factor case. The main effect plot shows what happens to the average response as we change factor levels. We decide on interactions based on the degree of parallelism. If the lines are parallel, then there is not a significant interaction. Since we do not get any indication of experimental error, we should only use these plots as an indicator for what might be happening. Here is an example of a main effect plot. Notice that the average response I on the vertical axis and the factor levels are on the horizontal axis. It is very important for you to realize that if there is an interaction present, then you shouldn't just average over the other levels of the other factors. This means that it is the interaction plots that you should be looking at, not the main effect plots. Here is an interaction plot. Notice that the levels of one factor are represented on the horizontal axis, while the levels of the other factor are represented as the different types of lines. The legend to the right indicates which lines belong with which factor. The average response is on the vertical axis. Notice that this situation is considered a one factor at a time experiment. Here is what the experiment looks like. Recall that a factorial experiment is one where each of treatment combinations is included in the experiment. It should be obvious from the picture that this is not the case for a one factor at a time experiment. Now, based on these three runs, we can get the effect for A and B. The problem here is that we need to take into account experimental error. By doing this, we would need at least 2 observations at each point, which means 6 overall. This would allow us to take an average of 2 points to get the main effects. For the factorial, we add a 4th treatment combination. Now, based on the 4 points, we can an average for the main effects for both A and B. So we are getting the same info in less runs. The relative efficiency is the number of runs for the of@ versus the factorial, which in this case is 6 divided by 4 is equal to 1.5. We can see from the plot that as the number of factors increases, the factorial design has a major advantage over the of@ design. The other disadvantage of a of@ design is that you can't estimate interactions. Based on this plot, even though AB plus and A plus B gave better responses than AB dash, A plus B plus does not yield better results, which is what you would expect. This, of course, is because of the interaction effect. We can extend the SS and DF principle from a one-factor situation to a multi-factor situation. You should be able to see that the sum of all of the SS for the factors would be equal to the SS for treatment if we decided to run this as a single treatment effect model. Here is the ANOVA table for a two-factor experiment. Here are the EMS for this situation. Notice that since these are fixed under the null, we create our test statistic based on the MSE. When the factors are qualitative, we can use regression models and response surfaces to our advantage. Here is an example of a two-factor case. We need to find out which effects are active. Based on the above with alpha equals 0.05, it seems that all effects are active. From this, there does not seem to be any issues with normality, but I would at least check the rule for equal variances. Based on the values found for the ratios, I would conclude that the equal variance assumption is valid. The main effect plots seem to mimic the output from the ANOVA. Also, realize that we can see a relationship in the temperature variable since it is quantitative. Since the interaction is significant, we should not use the main effect plots to decide on factor levels. Here is the interaction plot with temperature on the horizontal axis. Notice that these lines are not parallel. Also, based on this, to maximize lifetime, we should use material type B at temperature of 15. We could also have created the plot with the material type on the horizontal axis. This still leads us to the same answer. Above are the conclusions. We can create 3 types of contrasts. These are just the one-way ANOVA model contrasts. These allow us to determine if the lines on the plot are parallel by utilizing the hypothesis that the above contrast is equal to 0. If we take the DF from the ANOVA table for each individual interaction and break them into 1 DF tests, they would be equivalent to the hypothesis tests above. The above work just shows you that the equality on the previous page holds. We can use these contrasts to see if the line on the main effect plot is horizontal. If it is, it means that each of the means corresponding to those factor levels are equal. If we break the DF from a particular factor from the ANOVA table and break it into 1 DF tests, they also would be equivalent to the hypothesis tests above. We use orthogonal polynomials to see if there are relationships between the response and factors or interactions for factors that are quantitative. We can split these up into their respective orders. For example, if the factor has 3 levels, then we get a contrast for the linear and quadratic piece. We do the same thing for an interaction. Now that we know what contrast coefficient to use, we can create CICE or hypothesis tests for the contrasts. The only difference between this situation and the one we saw previously is that we need to adjust the variance for the presence of the other factor. We do this by including the number of the levels of the other factors in the denominator of the variance calculation as seen above for the 2-factor case. Here is an example of a 2-factor experiment in which we wish to set up trend contrasts. First, look at the headers. Across the top, we have split the factors and interactions into their respective linear and quadratic pieces. Then we have the ij terms along the horizontal. This is an indication of which level belongs with which factor, I for A and j for B. By looking at the orthogonal polynomial table, we would get the following for the A linear, B linear, and quadratic. Now we get the interaction terms by multiplying the respective columns together. You should make sure that you can do this. Sometimes we don't have replication for an experiment. We call these single replicate experiments. The problem here is that we do not have any DF left to estimate error. We will first look at orthogonal contrasts. Contrasts are orthogonal if their covariance is 0. This can be determined by finding the interproduct of their contrast coefficients. If this is 0, then the contrasts are orthogonal. So with a levels, we can create a 1 orthogonal contrasts. This is similar to orthogonal polynomials, except in this case the contrasts are not set up to determine model order. Of course, we have to assume that a certain number of the contrasts are negligible. This is usually done with higher order contrasts. So here we will use an f-test to decide if we have a significant interaction. If you find that the interaction is not significant, then you need to use the entire interaction as the error term, not just the ones you deemed inert to test the interaction. Here is an example where we will assume that any order term larger than 4 is inert. Here are the results. Here is the data step in SAS. Notice that we set the main effect terms and use them to calculate the interaction terms. Here is the line statement that gets the data in. Notice that we include the contrast coefficients for the main effects. Here is the SAS code to fit the initial model. We do not include the class statement since we want all of these terms to be considered quantitative. Here are the initial results. Now we need to pool the entries for the interactions. You should conclude that there is not a significant interaction. Now we should fit the model with the interaction term as the error. Tukey's test is typically used in most situations. It is fine as long as you realize that the interaction must be a function of the product of the individual effects. Here is the formula for the SS and how you now get the SS for error. Here is the test statistic. Notice that the critical point has 1 and A1, B1, -1 DF. If you have more than 2 factors, everything that we talked about gets extended to K factors. Here is the ANOVA with EMS. Next time we will talk about random effects models with two or more factors and mixed effect models.